Hey there, Algebra 1. We are going to try to jump into the rest of chapter 11 here and kind of throw multiplying and dividing radicals together. So it's a little bit more, but don't be overwhelmed. We're not going to go very deep into each one of them, okay? Focus on doing your best. Give me your best effort. We'll review some of this next year, but please give me your best effort. I know we're getting to the end here, so hang in there. Push hard, finish strong, okay? All right, so to multiply and divide radicals, we have a couple different rules here that we're going to follow, and then we'll kind of practice with some. So in order to multiply, we need to have the same type of a radical. So it has to be a square root times a square root, or it could be a cubed root times a cubed root. And what I mean by that is if you had like the square root of 2 and the square root of 4, you could put those together. But if you had the cubed root of 2 times the square root of 4, you can't do anything with that. You could take the cubed root of x and the cubed root of y and do something with that. Okay, so basically your index or the number in your radical, now for a square root there's kind of an invisible 2 there. They just have to be the same, and if they're the same then you can combine them. Okay, that's what this n means. As long as the number, or no number there, meaning it is a 2, if there's no number there, or if there is, as long as it's exactly the same, then you can put them together. Same for division. Okay, so when we divide, we need to say, okay, if there is a fraction underneath my radical, the radicand underneath the radical here, I can apply it to the numerator and apply it to the denominator separately. So if you see something like this, that means we could also kind of back and forth go either direction. Now there's one little thing that we have to talk about with division. We have to make sure that we don't have any radicals in the denominator because they just, math rule, don't like it, okay? All right, let's start with multiplying. This is a little bit easier. Let's kind of zoom in here. Okay, so if we had the square root of 2 times the square root of 6, first thing to do is look. Do I have the same either no number or number here? Yeah, they're both square roots, so I can combine these. And I could say that this is the same as the square root of 2 times 6, which we know 2 times 6 is 12, so we know it's the square root of 12. Okay, now the square root of 12, as we did before, can be simplified a little bit further. Now, is there any perfect square in here? 4 is a perfect square, and if I took it times 3, I would get 12. So the square root of 12 is equal to the square root of 4 times 3. But that means I really have the square root of 4 and the square root of 3, but this here turns into a 2, right? So I have 2 times the square root of 3. Okay? All right. Now this, again, right here, kind of going from this to this, was applying that rule backwards. I can just kind of say, okay, I'm going to take the radical of this part and the radical of this part. As long as they're joined by multiplication, you can do that. Okay, this one's going to be a little bit trickier here. Now, I'm going to just take the beginning numbers and I'm going to put them together. And then I'm going to put the radicals together separately. So I'm going to say a negative 2. Let's see if I can't change this a little bit. Okay, negative 2 times 5 times the square root of 18 times the square root of 50. Well, I know this gives me a negative 10 in front, right? This section here. And now I can say I'm going to multiply those two together. Now, it's not always helpful if I have to multiply them together and then, like I did up here, multiply them together to get 12 just to find different factors that they have. So I multiplied these 2 and 6 to get 12, and then I kind of had to divide it back up into different factors. So we don't have to do that. We can just kind of leave it like this and then come up with the factors. So this is where a factor tree would make a lot of sense here. So I know right away I see 2 and 9. I could turn that into 2 times 9. And the reason I want to get 9 there is because I know that 9 is a perfect square. Is there a perfect square in 50 that you can think of? Remember, your perfect squares are 1, 2, 4, 9, 16, 25. 2 times 25 would give you, is that going to go? Okay, 2 times 25 is going to give you 50. So what I can say here is that I actually have negative 10, and instead of writing 18 times 50, I'm going to write it this way. I'm going to say 2 times 9 times 2 times 25. Make sure it's all under the radical. Okay, well, I'm going to look at it and say, hey, the square root of 9 is actually 3. The square root of 25 is actually 5. And now that I have two 2's under there, the square root of 2 times 2 is actually just 2. So I can take everything out from underneath the radical in this case. So now what I have is negative 10 times 3 times 2 times 5. And when you multiply all of that through, you would get negative 300. So that's your final answer. Often you will have a radical left over like we did earlier. I had 2 times the square root of 3, but now I just have a negative 300, okay? It's possible as well. Okay, let's try another one. We've got 2 more to look at. This has a cubed root, so look real closely. If I have a cubed root, I have to have another cubed root to combine, and I do. So I can say that this is equal to the cubed root of 54 times 4. Okay, now 54 isn't a perfect cube, and 4 is not a perfect cube either. I'm looking for 3 things that multiply by themselves. Now in this case, I set it up so that it would multiply through and kind of give me some easy numbers. 54 times 4 happens to equal 216. Now 216 is uniquely a perfect cube, so this is the same as, taking 6 times itself 3 times. So 6 times 6 is 36, and 36 times 6 is 216. So, maybe that was a bad choice of numbers here. So, I can just say that the cubed root of 216 is 6. Okay, now it has to be a positive 6. You can't have one or the other there. All right, move this out of the way so we can do our next one. So, I guess that was our answer. I didn't get to that point. That's my answer. All right, last one. This one doesn't have anything to combine at all, but I do want to look at this and see if there's anything I can pull out. This is essentially the cube root of 4. I'm sorry, that's the square root of 4. You might see it as just the square root of 4x y squared. Those are the exact same thing right here and here are the same thing. Okay, so this is really the square root of 4 times the square root of x times the square root of y squared. Okay, so we're kind of using our rule backwards this time to separate it by factors and apply the square root to each one of those. Well, this I know I can turn into a 2. I can simplify it, and this can turn into simply a y. So my final answer here, I still have the square root of x. I can't leave that out. It would be 2y times the square root of x. That would be the most simplified version of that last example. Okay, now I'm going quickly here. Let's jump to division. I'm trying to keep this short so that you're not spending too long on this. Okay, division. Do you remember my rule? First thing I want to do here is probably rewrite it as a fraction. Remember, my rule was a fraction. So let's rewrite this. We're going to rewrite this as the square root of 3 divided by the square root of 6. Okay, we're going to write it that way. Now, I guess the rule says that if I had, well, I guess we should check here. Do we have the same? Is it both the square root or both the cubed root? Yeah, they're the same, so I can combine this. The rule says that I could put that together as a fraction. Okay, these are equivalent. I can go back and forth between this, and they're exactly the same thing. The reason I might want to combine them under the same radical is because 3/6 should make me think 1/2. I can simplify that a little bit. So that gives me the square root of 1/2. All right, well, I can't really have a fraction underneath the radical because technically this is the square root of 1 over the square root of 2. And I can't have a radical in the denominator. So this is what we call rationalizing the denominator. Okay, to rationalize the denominator means that we're going to have to multiply by something in order to get rid of the denominator from the square root from the denominator. And what we know about a square root, if the square root of 2, is unsquaring that 2. So if I took the square root of 2 times the square root of 2, what's going to happen? If I square something that I've unsquared, yeah, I just get 2. All right? Now, this is some real number, but it's an irrational number. It'll go on forever and ever. But uniquely, that number times itself will give me a whole number, an integer. All right. So let's go back to the example that we were doing. We had the square root of 1 over the square root of 2. Do you remember that from our example? Well, I don't want to have this radical underneath in the denominator here. So I'm going to use that same philosophy, and I'm actually going to say, if I multiply this, now I can never multiply anything and just say it's equal. But if I multiplied it by 1, the rule says that that's equal, right? If I multiplied, well, anything by 1, right? Let's say I multiply this by 1. Well, don't I still get the exact same thing? So is there another way that I could write the number 1 that might help me out here a little bit? Yes, there is. What if I wrote it as the square root of 2 over the square root of 2? This here is essentially the same thing as multiplying by 1. This is a big 1. Well, the square root of 2 times the square root of 2 in a denominator here, fractions we multiply the numerators across and the denominators across, is going to give me just a whole number 2 in the denominator. And this is going to give me the square root of 1 times 2, which is the same thing as the square root of 2 over 2. Now this can be our final answer because we have rationalized the denominator. We've made it into a rational number in the denominator. Okay? All right, so let's go back to our other examples here. Let's try this one. 25 times the square root of 3 all over 9 times the square root of 15. Well, when I look at that, there's really nothing I can simplify right away, but I need to recognize that I have I guess there is something I could simplify right away. I have a square root in the denominator, so I'm going to need to get rid of that. I'm going to need to rationalize that denominator. But actually, I can do something here. I can take my rule that I learned about multiplying. Oops. There we go. And I could say that this is really the same thing as 3 times 5. Or I could say that this is 25 times the square root of 3 all over 9. The square root of 3 times the square root of 5. See how I can apply that rule to both of them? Now, if I have a square root of 3 on the top and I have one in the denominator, that is going to cancel. Okay? So I can then say I actually just have 25 over 9 times the square root of 5. But because I don't want that square root of 5 there, I'm going to have to rationalize the denominator, which means I have to multiply by 1. And that's not going to help me get anywhere. I need 1 to look a little bit different for me. I need to multiply by the square root of 5 over the square root of 5. Okay, and when I do that, I'm going to get 25 times the square root of 5 for my numerator. And my denominator, I'm going to get 9 times the square root of 5 times the square root of 5, which we know to just be 5. And I'm going to leave it as 9 times 5 for a minute because I think you should see real quickly that I could simplify this a little bit. As long as everything is joined by multiplication, I can reduce. So I can divide both of these by 5. 5 divided by 5 is 1. 25 divided by 5 is 5. And there, finally, my final answer is 5 times the square root of 5 over 9. That is my final answer. Okay, so actually let's kind of move this up here so we can see where we started. These here are equivalent. Okay? Alrighty, I know these are tricky. The ones that you have tonight are a little bit easier. They're going to be a little bit more like this. So let's look at one like this. My first thing I need to do is recognize that I can not really simplify anything here. A 5 and a 7, they're both prime numbers, so there's not much I could do. They're also both under a radical, but they both have the same radical, right? It's a square root for the numerator and the denominator. So I can just jump to rationalizing the denominator. I don't want a square root of 7 in the bottom, so I'm going to multiply this whole thing by 1. And 1 is going to look different. It's going to be the square root of 7 divided by the square root of 7, which we know anything over itself is 1. So now in the numerator, I'm going to have the square root of 5 times the square root of 7. Use that multiplication rule right there. All over 7. Or the square root of 35 all over 7. And that's as far as you can go. Let's try another one simple like that, and then we are going to be done. All right, let's try this one here. It's our last one. I have I have two things here. When I look at this, I think, I've got a 5 in here. A square root of 5 times the square root of 2 would give me the square root of 10. And I've got a square root in the denominator. So maybe I could just kind of cancel some of those before I do anything else. Now, if you can cancel it before you do anything else, save yourself the headache. Do that instead of trying to rationalize the denominator. So there are two things you could do. I'm going to show you the easy way first, and then I'll show you the other way. If we want to change this to say 2 times the square root of 5, and then leave the denominator the same, I can apply the rule that says I can take the square root of 2 times the square root of 5. Which means I have a square root of 5 in both my numerator and my denominator, so they will cancel. And my final answer would just be what's remaining here, or the square root of 2 divided by 3. And my denominator does not have a radical, so it is rationalized. Now, if you don't want to split it up that way, you could do exactly what we did before. You could say, I'm going to actually just kind of rationalize that denominator right away. And you can do that. It'll take you a little bit more work, but you can do that. Square root of 10 over 3 times the square root of 5. And you say, hey, I see that radical in the denominator, and I'm going to multiply by a 1. Go ahead and do that. Okay, this is our 1, right? So that gives us the square root of 10 times 5. They're both under the radical. I'm combining them based on our multiplication rule there. And I'm going to have 3 times the square root of 5 times the square root of 5. Well, I know that just gives me 5 itself, right? So I'm going to have the square root of 10 times 5, I'm going to leave it like that for right now, times 3 times 5. Now, I know that I can pull there's some perfect squares up here, okay? So I'm going to turn this into, let's see, that would give me a 50 underneath the denominator, right? And 15 in the bottom. And what else can I do with this? Well, a 50, well, I could multiply that back out and say 25 times 2 is 50. Why would I want to take that 25? Well, because I know that's a perfect square. So what could really happen here is I could say this is the square root of 25 times the square root of 2 all over 15. And this here turns into just a 5. Okay, and now I can still reduce a little bit more, right? I could say 5 divided by 5 is 1, and 15 divided by 5 is 3, which gives me what is remaining. So I would get the square root of 2 all over 3. Isn't that the same answer we had last time? It sure is, and yet a lot more work, you can see. We had this amount of work here, or we had this amount of work here. Okay, but same answer. Neither one is wrong. It just takes a little bit longer. Okay, well, try a bunch of these on your own. Please reach out if you need some help. And I hope this helped a little bit. I'll see you guys later.